Okay, so we're going to move on to section 2.3, which is about arithmetic operations on matrices. And sort of for now on, we're mostly going to look at matrices without this. So you remember there was like some vertical line representing equals. We're going to really look at matrices for a while that don't have this vertical line. So we look at matrices. I mean, basically, this vertical line was just kind of representing equals. But yeah, so just to be clear, we're going to look at them without the vertical line. So for example, matrices like this. Okay. And we're going to answer questions like, you know, what does it mean to add, subtract, or multiply two matrices? Okay. And to be honest, it's not going to really be clear why we care about most of these things at this point. But at the end of the course, we're going to be doing something called Markov chains. And in order to study them, we're going to really need to understand things like matrix multiplication. So at this point, we're just going to learn how to do these operations just for the sake of it. But later, we're going to see applications of it. But for now, we just need to know like what it means. Okay, so first I need to talk about the size of a matrix. So this matrix, for example, okay, I can see that there's 6 entries in it, right? You might think, okay, maybe the size of this matrix is 6 or something. But actually, it turns out when we talk about the size of a matrix, we usually need to know more information. So we need to know how many rows and how many columns. So the size of this matrix, we say, you know, so this is a matrix of size 2 by 3, where 2 is the number of rows and 3 is the number of columns. Okay. So you have to remember this order. You always write the number of rows first, the number of columns second. Okay. So it's not, yeah, this x here is not really, it's not really times, it's more like, you know, so you read this as, you know, not 2 times 3, but 2 by 3. So it's a 2 by 3 matrix. Okay. Some special types of matrices are things which are like, you know, just have 1 row or 1 column. So, so this matrix, for example, if I do, 1, 2, 0, so it's a 3 by 1 matrix. Okay. And so when you have just 1 column, we call this a column matrix. So we call it this a column matrix because it only has 1 column. Okay. And then similarly, if I have a matrix like 0 to -4, 3 over 6 or 3 over 5, let's say. Right, so this is a one row, 4 columns matrix. So 1 by 4 matrix, and we call this a row matrix because it only has 1 row. Okay. So this is all just kind of terminology. So these are kind of special types of matrices, right? If you just have 1 column or 1 row, and yeah, these are going to come up at various points. Another type of special matrix is a square matrix. So a matrix is a square matrix basically if it looks like a square, which kind of means like not a rectangle. So basically if you have the same number of rows as columns, then it's square. So if the number of rows is equal to the number of columns. So for example, this matrix, right, is 2 by 2. 2 rows, 2 columns, that's a square matrix. 3 by 3. Right? And then the simplest possible matrix, right, is just a 1 by 1. Right? So this would be a 1 by 1. So this counts as a matrix, right? Even though it just has 1 row, 1 column, 1 element, or 1 entry, that's still a matrix. Okay. So actually, if you have a 1 by 1 matrix, it's square. It's a square matrix, it's a column matrix, and it's a row matrix, all in one, in some sense. But yeah. Okay. Any questions about any of this terminology? Okay. So, okay, now when we talk about rows and columns, the rows and columns are sort of numbered in a sense. So you have a first row, which probably you can imagine here, the first row is the top row, the second row is the second to the top, the third row is the third to the top, which is the bottom row, and your columns are numbered from left to right. So first column, second column, third column. So the rows and columns are numbered so top to bottom and left to right. Okay, so if I, for example, say, I take, if I say A is the matrix 2, -1, 4, 3, -1, 8, 1, 2, 9, like this. If I say, what is the first row of A, the answer would be this 1 by 3 matrix, 2, -1, 4. Right? So just like literally the first row is the first row, right? The top row. If I say the third column of A, it would be this column matrix, which is 4, 8, 9. Okay. So this is just saying, this is just kind of clarifying what it means. Yeah, if I say the first column, the second column, the third column, there is an ordering to these. Columns are left to right, the rows are top to bottom, right? So there's a kind of nice notation for talking about entries of a matrix. So if the matrix is A, so for a matrix A, we often write Aij for two numbers I and j to be the entry on the ith row and jth column of A. So we use like a little a ij to mean like one of the entries. And if your matrix was called B, you know, capital B, then you might use like Bij, right? And I think it'd be clear what you mean by that. It would, yeah, so so it would be clear. So for example, if it was called B, I would use Bij, right? To be the ith row, jth column entry. So in this case, like if I said A12, for this specific matrix here, this is the entry on the first row and second column. So I go to my first row. My first row is 2, -1, 4. I go to my second column. If you think about it, you know, the first row, second column, there's only one entry that's in the first row and the second column. It's this one. So I'd say that's -1. And for example, A13, right, would be 4. A31 would be 1, right? Third row, first column is 1, and so on. Any questions about that? Oh, sorry. Yeah, then your notation gets pretty annoying, right? If you, yeah, essentially in this course, we'll never see anything like that. However, if you were in that situation, you might want to start using like a comma, like AI, comma J or something. And then it's like now clear that, yeah, I am kind of aware that this looks like a 12, not a 1 and a 2. But to be honest, my personal preference would be to put a comma between these things, but your textbook doesn't do that. So I'm not putting a comma. Yep. So I is just a number, right? So I'm just saying for any number I, and for any number j, Aij means the element on the ith row in the jth column. So I is just, in this case, I would be 1 or 2 or 3 to indicate first or second or third, and j would be 1, 2, or 3 to be the first, second, or third column. Yeah. But yeah, so basically, you should just think about, like, if I plug in something for I and j, what does it mean? It means third row, first column, or whatever, depending on what you plug in. Any other questions about that? Yeah. That'll be fine. We'll okay, I have no idea what's going to happen on the quiz because this Pearson system is a mystery to me. But on a test or something, if you put a comma, we will understand totally what you mean. It'll be fine, yeah. Any other questions? Okay. So actually, what we're going to do, we're going to learn how to add, subtract, and multiply matrices. But actually first, there's something even more fundamental, which is just to say, what does it mean for two matrices to be equal? So for matrices, A and B, if I write A equals B, well, that means a few things. So it means that, first of all, for A to be equal to B, they have to have the same size. So it means A and B have the same size. But obviously that's not good enough. We also need, additionally, the corresponding entry of A is equal to the corresponding entry of B for all entries. So the corresponding entries of A and B are all, equal to, are all equal. So in other words, I mean, this really is as simple as it seems. Like, if this matrix here is equal to another matrix, well, that matrix has to be 2 by 3, and it has to have all the same numbers in all the same places, right? So to be equal, they have to have a 2 here, a 3 here, a -1 here, 0 here, 1 here, 2 here. Like, they have to be the same size, and every entry has to be equal. Okay, so adding now if we want to add two matrices, well, there's sort of a rule here. So to add two matrices, A and B, well, then A and B have to have the same size, okay? So they have to have the same size. And remember, when we talk about size, I'm not just talking about how many entries there are. I'm talking about the exact same shape. So the exact same number of rows, the same number of rows, same number of columns. Okay. But then, if they have the same size, then adding two matrices is kind of the obvious thing. You just literally go through the entries and add them up. So, if they have the right size, so to get A plus B, you just add each individual entry. Okay, so as an example, let's say A is 1, 0, 3, -2, and B is equal to 4, 1, -3, 8, right? If I wanted to get A plus B in that example, well, first of all, you got to think, does this even make sense? And in this case, it does, right? These are both 2 by 2. Okay, so it makes sense to add them. And when I add them, I just add the corresponding entries. So here I get 1 plus 4. Here I get 0 plus 1. 3 plus -3. and negative 2 plus 8. So in other words, it's 5, 1, 0, 6, right? Okay. However, as another example, if I said A is, you know, let's say A is this matrix and B is this matrix. Well, so this is a 3 by 2 matrix. This is a 2 by 3 matrix, right? If you think about it, they've got the same number of entries. Each of them has 6 entries, but that's not good enough, right? So in this case, for this A and B, A plus B is not defined. Okay, so if somebody asked you to compute A plus B in this case, it'd be a trick question. You should just say, I can't do it, it's impossible, there is no such thing as A plus B in this case, right? Any questions about that? Okay. So, okay, so that's adding matrices, but you can also subtract matrices, and the operation is the same, basically. So to subtract 2 matrices, they have to have the same size, and then to subtract them, you just subtract every individual entry. So if I'm doing this example again, this one here, so here A minus B would be, so here I've got 1 minus 4, 0 minus 1, 3 minus negative 3, and negative 2 minus 8. So I get negative 3, negative 1, 6, negative 10, right? Okay. So let's do a little example involving some of these operations. Okay, so I think you'll be able to compute them again. Take this minus this minus this, yeah. So here's an example. Okay, if you want, I'll do it. So solve for x, y, z, and w in the equation so here I've got x, negative 2, 3y, plus negative 2, z, negative 1, 2, equals 4, negative 2, 2 times w, and 4. Okay. So yeah, so here all this really requires is for you to understand how does matrix addition work, so that I can kind of add these two things together, and how does equal work with matrices. Okay, so the left side, I can combine these two, right? So this is the same as, so to add these two matrices, I just add the entries. So x minus 2, z minus 2, right? This is minus 2 plus z, which is z minus 2. 3 minus 1 is 2, and then y plus 2. And then the equation says this should equal 4, negative 2, 2z, or sorry, 2w4. So this is just saying, what does it mean to add these two matrices? It means this, right? And then we ask ourselves, what does it mean for this matrix to equal that one? And again, it just means every entry is equal to the corresponding entry. So we end up with x minus 2 has to equal 4. Z minus 2 has to equal negative 2. 2 has to equal 2 times w. And y plus 2 is equal to 4. Okay. And then at this point, you can just read off the answer, basically. So x is 6. Z is 0. W is 1, just by solving each of these equations. Y is 2, right? So that would be your solution. By the way, you might see some, when you're going through old versions of test 2, I'm pretty sure you'll see some questions like this. Obviously, different years, we cover different stuff at different times in the course, so this is not on the test next week, but now you know how to do it anyway, right? So by the way, the test next week is up to what we did yesterday. Okay. So that's addition and subtraction and equals. Let's now talk about something called scalar multiplication. Okay, so scalar multiplication is just a fancy word for multiplying a matrix by a number. Okay. And it turns out there's no big surprises here. If I multiply a matrix by a number, all you need to do is multiply all the entries in the matrix by that number. So if I take, let's say, a half times 1 to negative 4, 0, 0, 3. Okay, so this is taking a number times a matrix. And all you do is kind of bring that number inside and multiply it by all the entries. So it's a half, 1, negative 2, 0, 0, 3 over 2. So generally, C times A is the matrix. You get by multiplying everything in A by C. So each entry by C, where C is a real number. Okay. Any questions about this? So by the way, you can also kind of do these operations kind of together, right? You can take, now that we know how to do scalar multiplication, we know how to do addition, You know, so if, for example, if I wrote something like, you know, 3 times the matrix A minus, you know, 2 times the matrix B times, you know, 3/4 or something, right? We'd be able to do this operation, right? You take A, you multiply it by 3, you take B, multiply it by 2, you subtract the matrices, that'll give you a matrix, and then you multiply the whole matrix by 3/4, right? So basically you can chain these operations together. Okay. So hopefully this stuff doesn't seem too bad so far. Where things start getting tough is matrix multiplication. Yeah. Yeah, exactly, yeah. So you got to kind of think of the right order of operations, but that's exactly what you would do, yeah. I'd apply the multiplication here, I'd apply the multiplication here, I'd then do the subtraction, and then I would multiply at the end, yeah. Yeah. Because I'm bringing in this 1/2 into everything, so that 1/2 gets multiplied by the 3, and then it's 3/2. So this is, yeah, this is just the number 1/2 being multiplied by everything in the matrix. 1.5 is, yeah, same thing, so that'd be fine, yeah, totally fine. Yeah. Yeah. Sometimes. Matrices have a lot of different kind of applications and purposes. So one of them is solving systems of equations, and we're going to come back to that at some point. So at some point, we're going to use something we'll learn about matrices, matrix inverses, to solve systems of equations. But we'll also use them for something called Markov chains. So sometimes they're not really about that. You know, matrices they can represent a lot of things, basically. Any other questions? But if you'd like, you can still think of them that way for now, right? If you wanted to. Okay, so like I was saying, where things start getting difficult is matrix multiplication. It's going to seem like a really, really weird operation. So when I say matrix multiplication, we've already done multiplication by a constant, by a scalar, like by a number. But now I want to say, what does it mean to multiply 2 different matrices? If you've never seen this before, then probably whatever you're thinking as the answer to this question is possibly the wrong answer. So it's not the case. You don't just take the entries and multiply them all the way through the matrix or something. That's kind of the most obvious answer, but it's not the right answer, it turns out. So let's start with the simplest possible case, which is just multiplying a row matrix and a column matrix. So imagine I've got a matrix A, which is the matrix 1, -2, 3. And I've got the matrix, so this is a 1/3 matrix. I've got the matrix B, which is 1, 4, 0. So this is a 3/1. So how do you compute A times B? So what you do is you go through the row, you take the first element, and then you go through this column, and I multiply these two elements, okay? And then I add this times this, and I add this times this to make one by one matrix. So I take 1 times 1 plus -2 times 4 plus 3 times 0. So this is not like these are not separate entries. This is with a plus. So that's 1 minus 8, which is -7, plus 0. So the resulting matrix is this matrix, which is a 1 by 1 matrix. Okay. So generally speaking, like, so here, well, here, what I did was I took a 1 by 3 matrix multiplied by 3 by 1. And it's kind of important that these 3's are the same number because, so the number of entries here, like each entry here gets multiplied by an entry here. So the number of columns here has to equal the number of rows here. And what it gives you is a 1 by 1. So generally what happens is to multiply two matrices, you need the number of columns of the first one to equal the number of rows of the second one. And what you get as the result is whatever number you have here by that number you have here. So if A is, let's say, m by n, and B is n by k, then the product A times B is m by k. Okay? And you always need the number of columns of A to equal number of rows of B, or else A times B is not defined. Okay. So I haven't really explained how to do this like in general for bigger matrices, but this kind of explains how you do it if you have a row matrix and a column matrix. Right? So if this was 10 entries long and this was 10 entries high, I would just take the first entry, multiply, and just add the numbers up. I get a 1 by 1 matrix. Okay. So let's now see an example maybe of a slightly bigger matrices. Or are there any questions about this? Yeah. Not necessarily. So, well, if your first matrix is a row matrix, the other one's a column matrix, then yes, it will be. But generally, if this was like, well, let's see an example where it's not. So let's say that A is 1, -2, 3, 0, 1, 1. So a 2 by 3 matrix. maybe just to keep things simple, I'll make this one a column matrix. So it's 1, 4, 0. Okay. So this is 2 by 3. This is 3 by 1. Okay. If we're asked to compute the product of these, the first thing you should do before you start calculating is you should say, does this even make sense? Like, does it make sense to multiply this matrix by that one? And the answer is yes, because the number of columns here is 3. The number of rows here is 3. And these numbers are the same. Okay. And so that's the first thing to check. And so therefore it does make sense. So therefore AB makes sense. It exists. And then I kind of look at my other two numbers, and that tells me how big the product is going to be. So this product is going to be 2 by 1. You can kind of think of that as sort of canceling out these two numbers that are the same. And your product is always like, yeah, the 2 kind of left over here and the 1 here is how big the product will be. So this is going to be 2 by 1. 2 rows, 1 column. Okay. So here's how I compute the first row. I basically do something similar to what we did over there, but ignoring the second row of A, kind of. So I take my first row of A, 1, 1, -2, 4, 3, 0, right? So the same way I did it on the previous one. So my first row will just have the number 1 times 1, -2 times 4, 3 times 0. Okay. And then my second row is going to be, like I do the same thing, but with the second row of A. So I take 0 times 1, (1 times 4) plus 1 times 0. So at the end of the day, I get -7 here, 4 here. So this is indeed a 2 by 1 matrix, right? Yep. So when you're kind of adding these things all together, order doesn't really matter because, you know, x plus y is the same as y plus x. You can always switch these orders. But probably to do things in a systematic way that you can always remember, probably it does make sense to, yeah, to do it. This one, you know, this one kind of going across in order makes sense, but yeah. Oh. That's a really good question. In this case, B times A does not exist. So A times B makes sense because it's 2 by 3 times a 3 by 1, and the 3's match. But B times A, in this case, does not exist. Okay, because the number of columns of B does not equal the number of rows of A. Right, because B is 3 by 1, A is 2 by 3, and these numbers are not the same. But that's a really good question, yeah. Okay. Any questions about this? Yeah. So the number of columns of the first one must equal the number of rows of the second one. Yeah, so You always need number of columns of A to equal number of rows of B if you want to do A times B. Yeah. And then what you end up with, the size of the resulting matrix will be the number here by the number that's here. It's kind of a weird operation, right? Maybe I'll just add a little bit to this example. So let's say A is the same as before. But now B, I'm just going to add another column. So 1, 4, 0. And then 0, 2, 3. So can anyone tell me how, so now if A is the same as before, that one over there, B is this, what's the size of the matrix A times B going to be? So something by something. Yeah? Yeah. Right, 2 by 2, because this one's 2 by 3, this one's 3 by 2. These numbers match, and then the remaining numbers is the size of your new matrix. Okay. Okay, so now, I want 4 different numbers here, right? It's going to be a 2 by 2 matrix. If you think about it, my top left thing here, so to compute that, so I want the entry in the first row, first column of A by B. What you do is you take the first row of A, and you do this kind of multiplication, adding thing with the first column of B. But that's something we've actually computed now twice. So the first row of A kind of times the first column of B will give me -7, right? That's this 1 times 1, -2 times 4, 3 times 0. The entry in the second column, second row, first column. I take the second row of A, the first column of B. I do this multiplication thing. I get 4. So these are the same numbers as before, right? Things only change when I go to the second column. So to get the first row, second column, what I do is I take the first row of A and kind of multiply it down the second column of B. So I get 1 times 0 plus -2 times 2 plus 3 times 3. Okay. To get the second row, second column, I take the second row of A and kind of multiply it down the second column of B. So 0 times 0 plus 1 times 2 plus 1 times 3. Okay, so at the end I get -7, 4, nothing, -4 plus 9, which is 5, right? Yeah, that matches what I wrote here. So, okay, so that's just a bit of introduction to that, but we'll continue doing more examples next time.